In this illustration, we are given two tracks, each of mass capital M, are moving without friction in opposite direction on the adjacent parallel track with the same speed, same velocity u. You can observe here in this figure, this track number 1 is moving in the rightward direction with the speed u, it is having mass capital M. Track number 2 is also moving in this track, parallel track, with the same speed u, and it is also having mass capital M. One is carrying potato and other is carrying onion. Suppose this is carrying potato and this is carrying onion. A bag of the potato has mass m1 and a bag of the onion has mass m2 included in the masses of the track capital M. That means this m1 or m2 both are included in capital M, right? That means capital M is the mass of the track plus bag of the onion or potato, and similar statement for this also. In next part of the question, it is given when tracks get close to each other while passing, the drivers exchange a bag with the other one by throwing the other one. Find the final velocities of the track after exchange of the bags. We need to calculate the velocity of the both tracks after exchanging the onion and potato bags. So let us make the diagram to the next page. This is the situation. Now let us analyze the forces, type of the forces acting on the system. It is given there is no friction anywhere. That means there is no external force acting on any of the track in the horizontal direction. That means both tracks moves without friction. There is no external force acting any of the track in the horizontal direction. That means the linear momentum of any of the track will be conserved and always conserved in the horizontal direction. Okay. Now let us analyze what happens when they exchange the bag. This is the situation when they are crossing each other. This is carrying potatoes and this is carrying onion. Say this track number 1 throw bag of the potato like this, and this track number 2 throw the bag of the onion, and it is entered in the track number 1. Okay, that means the potato bag is removed from the track number 1 and entered into track number 2. Similarly, onion bag is removed from track number 2 and entered to track number 1. Okay, we know the tracks are moving with the speed u and u. That means while throwing, the velocity of the potato bag should also u in the horizontal direction, because bags are thrown in the direction perpendicular to the track. That means the speed of the potato bag in the rightward direction should also be u. That means the linear momentum of the potato bag should be equal to m1 u in the rightward direction. That is the same direction as the tracks move. And here we can observe this onion bag is thrown from this track number 2 perpendicular to the track direction. That means the velocity of the onion bag should also same as the velocity of the track. It is moving in the leftward direction. That means the velocity of the onion bag should also be u in the leftward direction. Leftward direction, that is in the horizontal direction, leftward. That means the linear momentum of the onion bag should be equal to m2 multiplied by u in the leftward direction. If we consider track number 1, what is happening? m1 u linear momentum is subtracted in the rightward direction and included the m2 u in the leftward direction. So let us analyze the linear momentum conservation principle in the horizontal direction, right? So first let us analyze this track number 1, right? Initial linear momentum when potato bag was not thrown, that is equal to capital M multiplied by u. Now this one, that is m1 multiplied by u, linear momentum is subtracted in the same direction. So linear momentum left in the system is equal to capital M multiplied by u minus m1u, and included linear momentum is equal to minus m2u. So linear momentum just before the process completed is equal to m capital mu minus m1u minus m2u, and after the process the truck with the onion bag move in the rightward direction with the common velocity. Say common velocity is v1, so the mass of this truck just after the process should be equal to capital M minus m1, and included mass is m2. So mass of the system of first truck should be equal to capital M minus m1 plus m2, and linear momentum should be equal to multiplied by its velocity just after the process. From this equation we can find the velocity of the truck number 1 in the rightward direction. This is equal to capital M u minus m1u minus m2u divided by capital M minus m1 plus m2. Now let us analyze truck number 2. Let us assume the leftward direction is positive direction. That means the initial linear momentum of the system, that is the truck number 2, is equal to capital M multiplied by u. The removed linear momentum in this direction is m2u, right? So linear momentum left in this system is equal to capital M multiplied by u minus m2u, and included linear momentum is m1u. This is the potato bag, but in the opposite direction. So linear momentum just before the process should be equal to capital M multiplied by u minus m2 multiplied by u minus m1 multiplied by u, right? And after the process the truck and the potato bag both move with the common velocity. The mass of the system after the process should be equal to capital M minus m2, because m2 mass bag was removed. So capital M minus m2, and m1 mass is included. So capital M minus m2 plus m1, and let velocity of this truck is v2 after the process. So linear momentum should be this one. From this equation we can find the velocity of the truck number 2 just after the process. This is equal to capital mu minus m1u minus m2u divided by capital M minus m2 plus m1. In this illustration it is given a railroad car of mass capital M is at rest on a frictionless track with the mass of man small m standing at its edge. In this diagram you can observe the mass of this railroad car which can move on the track without friction, and this man is standing at the edge of the right side edge, and this man is having mass small m. If the man jumps up from the car toward right with an initial velocity u with respect to car, find the velocity of the car after its jump. Now what happens? This man jump from the car in the rightward direction with respect to car with the velocity u, and here we need to calculate the velocity of the car after the jump. Okay, so let us analyze the situation. This is the car and man. If we take car plus man as system, we find there is no external force acting on the system in the horizontal direction. Why? Because there is no friction between the railroad car and track. That means no external force acting on the system, our system of the man and car, in the horizontal direction. But there is friction between the car and man. But it is an internal force, and we know these internal force does not interfere with the conservation of linear momentum principle. Okay, now let us assume the velocity of the car just after jumping is v, and it should be in the leftward direction, right? Why leftward direction? Because initially system is at rest and man is getting linear momentum in the rightward direction, and initial linear momentum of the system is 0. For making linear momentum of the system 0, car has to move in the leftward direction. So let us assume this velocity is v. The velocity of the recoil of the car is v. Now we need to calculate the velocity of the man with respect to ground, because in conservation of linear momentum principle, we should have the velocity with respect to ground. So now we can write the velocity of the man with respect to ground. This is equal to velocity of the man with respect to car plus velocity of the car, right? Let us assume rightward direction is positive direction, and this velocity of the man with respect to car is in the rightward direction, and this is having magnitude u. So this is equal to u, and velocity of the car in the leftward direction. So the velocity of the man should be equal to u minus v. Okay, and as we discussed, no external force act in the horizontal direction. So we are going to conserve the linear momentum of the system in the horizontal direction. Okay. Now we know the system initially at rest. If system initially at rest, that means P initial, that the initial linear momentum of the system equal to 0. That is P initial equal to 0, right? And according to linear momentum conservation principle, the linear momentum of the system just after jump should also be 0. So let us write the final linear momentum of the system, and man is jumping the rightward direction. This is the positive direction. So linear momentum of the man should be equal to small m multiplied by u minus v, and linear momentum of this car equal to minus m multiplied by capital V, and this should be equal to 0. Okay. Now we can calculate the value small v. We can rearrange this equation, and this value small v equal to mu divided by small m plus capital M. We can observe we have solved the similar nature problem in beginning of the discussion. We can find this velocity, that is the velocity of the recoil of the railroad car is same as the velocity of the plank when men walk on the plank. Why? Because same nature of the forces are acting in the system. Okay, and in that case also there is no external force acting on the system in the horizontal direction. In this case also there is no external force acting on the system in the horizontal direction. That's why the cases are same. Now let us move to next illustration. In this illustration we are given a railroad car of mass capital M with a man of mass small m is moving with a velocity v1 without friction. The man jump in the direction of the motion of the car with a velocity u with respect to car. Find the final velocities of the man and that of the car after jump. Okay. You can observe here in this diagram, this is a railroad car of mass capital M. This car can slide on these rails without friction, and initially man as well as a railroad car both are moving with the common velocity. This is equal to v1. Then what happens? This man jump from this side in the direction of the motion of the car with the speed u with respect to this railroad car. And here in this case we need to find the velocity of the man as well as car, railroad car, just after jumping. Okay, so this is the situation. So let us make the situation just before jumping when car as well as man both are moving with the common velocity v1. And this is the situation just after jumping. Man jump from this end with the velocity u with respect to car. While doing so, the velocity of the railroad car will change. Okay, let us consider the velocity of the man with respect to ground is v-man, and velocity of the railroad car will change from v1 to v2. Let us assume the direction remains same in the rightward direction. Okay, so here we assume the velocity of the car just after jumping of the man is v2. Now if we consider man and railroad car as a system, we find there is no external force acting on the system in the horizontal direction because there is no friction between the railroad car and rails. Okay, but there is friction between the man and railroad car, but this friction is internal of nature. That means it will not make any effect in the conservation of linear momentum of the system. Okay, so let us find the velocity of the man with respect to ground, because for conserving the linear momentum we need velocities with respect to ground. So let us write the velocity of the man with respect to ground. We can write the vector equation. We can write velocity of the man equal to velocity of the man with respect to car plus velocity of the car, right? And let us assume rightward direction is positive direction. So we can write velocity of the man with respect to car as u, and velocity of the car at this time is v2. That means velocity of the man should be equal to u plus v2. Okay, now let us conserve the linear momentum. Initial linear momentum of the system is capital M plus small m multiplied by v1, and final linear momentum include the linear momentum of this railroad car, that is equal to capital M multiplied by v2 plus linear momentum of the man, that is equal to small m multiplied by this value u plus v2. So let us apply conservation of linear momentum, right? Now we can rearrange this equation to get the value of v2. v2 is the velocity of the railroad car just after jumping. This is the velocity of the railroad car. If you calculate, you will find this value. For calculating the velocity of the man, you need to add v2 with u. So velocity of the man, this velocity is with respect to ground, this is equal to u plus v2. v2 is this value. If we substitute the v2 value here and calculate, we will find the velocity of the man should be equal to capital M plus small m v1 plus capital mu divided by capital M plus small m. So these are the velocities of the man and car just after jumping. Now let us move to next illustration. In this illustration, it is given two identical buggies, each of mass capital M, moves one after due to inertia without friction with the same velocity v0. A man of mass small m rides on rear buggy. You can observe here in this figure, these are the two buggies. This is the front buggy, this is the rear buggy. Both are having the same mass, and man is riding on the rear buggy. Man mass is small m, and both are moving with the same velocity v0 and v0 in the rightward direction. At certain moment, the man jump into the front buggy with the velocity u relative to this buggy. That means at certain time, this man jump to this front buggy with the velocity u with respect to the rear buggy. Here we need to find the velocity with which the buggy will move after that. We need to find the final velocities of the rear buggy and front buggy. You can observe here, after the process, this man will be on the front buggy. So here we need to find the velocity, that is a common velocity of the man and front buggy, and velocity of the rear buggy. So first of all, let us analyze the rear buggy. This is the rear buggy, and this is the situation just before jumping. At this time, man of mass small n and this railroad car both are moving with the common velocity, and there is no friction between the rails and railroad car. That means we find there is no external force acting on the system in the horizontal direction. That means the linear momentum of the system in the horizontal direction is conserved just before jumping and also just after jumping. Okay, so let us assume the velocity of the rear buggy just after jumping is Vr. Vr is the velocity of the rear buggy just after jumping. So we need to calculate the velocity of the man just after jumping from the rear buggy. This velocity should be velocity with respect to ground. So let us calculate the velocity of the man with respect to ground, and we know this equation, velocity of the man equal to velocity of the man with respect to buggy plus velocity of the buggy, and here we are analyzing the rear buggy only. And let us consider rightward direction as a positive direction. right? This is the positive direction. So we can write velocity of the man as u, this is the velocity with respect to buggy, plus velocity of the buggy, that is Vr. So velocity of the man should be equal to u plus Vr. Okay, as we discussed, we can conserve the linear momentum of the system just before and just after jumping. So initial linear momentum of the system of man and buggy should be equal to capital M plus small m multiplied by V naught. Okay, now come to the final linear momentum. System is same, that is a man and buggy, rear buggy. The linear momentum of the buggy just after jumping should be equal to capital M multiplied by Vr plus small m multiplied by Vman, and Vman equal to u plus Vr. So this is the final linear momentum. Initial linear momentum and final linear momentum both should be equal. So let us equate these two values, and if we solve this equation, we can find the value of the Vr. Vr is the velocity of the rear buggy, and this is equal to Vr equal to V naught minus mu divided by capital M plus small m. This is the velocity of the rear buggy just after jumping. As we know, there is no friction between the rails and railroad car. That means the velocity of the rear buggy will be constant always, and that is equal to V naught minus mu divided by capital M plus small m. Now let us consider front buggy. This is the front buggy just before landing. Now what will happen? Man, after getting this velocity, will land into this front buggy. At that time, front buggy is moving with the velocity V naught. That means if we take man and front buggy as a system, we find here also there is no external force acting on the system, right? And here we are considering man and front buggy as a system. So this is the scenario or situation just after landing, and just after landing, this man and this buggy both will move with a common velocity, and let us assume this common velocity is Vf. Okay, and let us consider this direction as a positive direction. Now we are taking our system, that's man and front buggy, and conserving the linear momentum in the horizontal direction. The initial linear momentum of the system is equal to capital M multiplied by V naught plus small m multiplied by u plus Vr, and final linear momentum of the system should be equal to capital M plus small m multiplied by Vf, and we have calculated the value of Vr. Vr value is V naught minus mu divided by capital M plus small m. So here we can substitute the value of Vr, right? This is the value of Vr. Now from this equation we can find the velocity of the front buggy. If we solve this equation, we will find velocity of the front buggy equal to V naught plus m capital M small m u divided by capital M plus small m whole square. In this illustration, it is given a disc of mass capital M and radius capital R is kept flat on a smooth horizontal table. आप देख सकते हो ये डिस्क है कैपिटल एम मास की, जिसकी रेडियस कैपिटल आर है, और इसको रखा हुआ है स्मूथ हॉरिजॉन्टल टेबल पे. ये हमारे पास ग्रीन कलर की सरफेस आप देख रहे हो, ये फिक्स हॉरिजॉन्टल सरफेस है. एन इंसेक्ट ऑफ मास स्मॉल एम, ये इंसेक्ट, इसका मास है स्मॉल एम, ए लाइट ऑन द पेरीफेरी ऑफ द डिस्क एंड बिगिन टू क्राउल अलोंग द एज. ये इसके पेरीफेरी पे लैंड करता है और इसके सर्कमफेरेंस में, पेरीफेरी में ये क्राउल करने लगता है एज के अलोंग. द क्वेश्चन इज डिस्क्राइब द पाथ ऑफ द सेंटर ऑफ डिस्क. हमें यहाँ पे सेंटर ऑफ डिस्क के पाथ को डिस्क्राइब करना है. साथ साथ हम लोग ये भी लर्न करेंगे कि यहाँ पे जो इंसेक्ट है उसका पाथ कैसा होगा, जो हमारा डिस्क प्लस इंसेक्ट है उसके सिस्टम का सेंटर ऑफ मास का पाथ कैसा होगा. इसके बारे में हम लोग यहाँ पे डिस्कस करने जा रहे हैं. तो चलते हैं हम लोग एनालिसिस पार्ट पे. ये हमारा डिस्क है, राइट. इस डिस्क में हम लोग अगर इसको सिस्टम ले लें तो क्वेश्चन में गिवन है देयर इज नो फ्रिक्शन बिटवीन द डिस्क एंड हॉरिजॉन्टल सरफेस. अगर हॉरिजॉन्टल सरफेस और डिस्क के बीच में कोई फ्रिक्शन होता तो हॉरिजॉन्टल प्लेन के पैरेलल किसी भी डायरेक्शन में एक्सटर्नल फोर्स होने की गुंजाइश होती, लेकिन यहां पे कोई भी फ्रिक्शन नहीं है। इसका मतलब क्या हुआ, हॉरिजॉन्टल सरफेस के पैरेलल या हॉरिजॉन्टल डायरेक्शन में हम लोग कह सकते हैं देयर इज नो एक्सटर्नल फोर्स एक्टिंग ऑन द सिस्टम। जबकि वर्टिकल डायरेक्शन में फोर्सेस हैं, लेकिन वो बैलेंस हो रहे हैं, क्योंकि वर्टिकल डायरेक्शन में हमारा डिस्क इंसेक्ट हमारा मूव नहीं कर रहा वर्टिकल डायरेक्शन में। इसका मतलब क्या हुआ, हम लोग कह सकते हैं देयर इज नो नेट फोर्स एक्टिंग ऑन द सिस्टम इन द हॉरिजॉन्टल डायरेक्शन एंड वर्टिकल डायरेक्शन। अगर ऐसी सिचुएशन गवर्न होती है तो हम लोग कहेंगे इनिशियली सिस्टम का जो सेंटर ऑफ मास है वो रेस्ट में था। जब इसने क्राउल करना शुरू नहीं किया था इंसेक्ट ने, तो यहाँ पे ये जो डिस्क का सेंटर था वो भी रेस्ट में था। तो हम लोग कह सकते हैं कि हॉरिजॉन्टल फोर्स के अपसेंट होने पे अगर सिस्टम का सेंटर ऑफ मास इनिशियली एट रेस्ट, तो सिस्टम का सेंटर ऑफ मास कभी भी रेस्ट में रहेगा, राइट। और ऐसी सिचुएशन कैसे पॉसिबल है कि अगर हमारा सेंटर ऑफ मास सपोज यहाँ पे है, दिस इज द सेंटर ऑफ मास, अब हमें सेंटर ऑफ मास को रेस्ट में रखना है। अगर सेंटर ऑफ मास को रेस्ट में रखना है और यहाँ पे मोशन हो रहा है इंसेक्ट का, कहाँ पे, ये क्राउल कर रहा है एज में, तो ऐसी सिचुएशन तभी पॉसिबल है जब सेंटर ऑफ द डिस्क भी सेंटर ऑफ मास के रिस्पेक्ट में रोटेट करे। तो हम लोग यहाँ पे कह सकते हैं कि बोथ द इंसेक्ट एंड सेंटर ऑफ द डिस्क मूव इन ए सर्किल ऑफ द डिफरेंट रेडियस। इसकी रेडियस होगी इतनी, सेंटर ऑफ मास से ओ तक की डिस्टेंस, दिस द रेडियस ऑफ रोटेशन ऑफ द डिस्क, और ये सेंटर ऑफ मास से इंसेक्ट तक की जो डिस्टेंस होगी दैट इज द रेडियस ऑफ द रोटेशन ऑफ द इंसेक्ट। तो पाथ ऑफ द रोटेशन ऑफ द इंसेक्ट सर्कुलर होगा कुछ ऐसा, राइट। दिस इज द पाथ ऑफ द मोशन ऑफ द इंसेक्ट, इस तरह से मूव करेगा। हम लोग कह सकते हैं कि ये काउंटर क्लॉकवाइज डायरेक्शन में मूव करेगा। अगर हम लोग यहाँ पे डिस्क के सेंटर को देखें तो सेंटर ऑफ मास ऑफ द सिस्टम को रेस्ट में रखना है, तो ये रोटेट करेगा अपोजिट सेंस में, राइट, इस सेंस में रोटेट करेगा यहाँ पे ऐसे, और इसकी रेडियस पर रोटेशन होगी R1 और इसकी इंसेक्ट की रेडियस पर रोटेशन होगी R2। अब हम लोग यहाँ पे रेडियस ऑफ रोटेशन ऑफ द डिस्क सेंटर कैलकुलेट करते हैं, राइट। इसका मतलब क्या हुआ कि हमें यहाँ पे सेंटर ऑफ मास से सेंटर ऑफ द डिस्क तक की डिस्टेंस कैलकुलेट करना है, दैट इज द रेडियस ऑफ द रोटेशन ऑफ द डिस्क, ओके। अच्छा, एक चीज और भी देख लेते हैं कि यहाँ पे ये मोशन कैसे हो रहा होगा। हमारे पास सबसे पहले सेंटर ऑफ मास यहाँ पे है, इंसेक्ट यहाँ है, सेंटर ऑफ द डिस्क यहाँ पे है। तो आप देख सकते हो कि सेंटर ऑफ डिस्क इस पोजीशन को स्टेशनरी रखना है हमेशा, ये स्टेशनरी है, और ये पूरा सिस्टम इस सेंटर ऑफ मास के अबाउट रोटेट कर रहा है, राइट। आप देख सकते हो कि सेंटर ऑफ मास ऑफ द सिस्टम स्टेशनरी है, जबकि इंसेक्ट और सेंटर ऑफ डिस्क इज रोटेटिंग इन द डिफरेंट सर्कुलर पाथ विद द डिफरेंट रेडियस। तो अब हम लोग लौटते हैं रेडियस ऑफ रोटेशन ऑफ द डिस्क कैलकुलेट करने में। R1 कैलकुलेट करेंगे। R1 डिस्टेंस होगी डिस्टेंस ऑफ द सेंटर ऑफ मास ऑफ द सिस्टम, दिस वन, फ्रॉम द सेंटर ऑफ द डिस्क, राइट। ये हमें डिस्टेंस हमें यहाँ पे कैलकुलेट करनी है। तो अगर हम लोग इसकी डिस्टेंस कैलकुलेट करना चाहें यहाँ से, तो वी कैन राइट R1, दिस R1 इक्वल टू स्मॉल m मल्टीप्लाइड बाई कैपिटल R डिवाइडेड बाई टोटल मास, राइट। हम लोग सेंटर ऑफ मास की डिस्टेंस यहाँ से कैलकुलेट करने के लिए फॉर्मूला लगाएंगे m1 R1 प्लस m2 R2 डिवाइडेड बाई m1 प्लस m2, राइट। नाउ लेट अस कैलकुलेट द वैल्यू ऑफ R1। इसके लिए हम लोग फॉर्मूला यूज करेंगे। RCM की डिस्टेंस सपोज यहाँ से R1 है, यहाँ पे हम अपने एक्सिस सपोज ले लें, इसको सपोज मैं x कह दूं, ओके। तो इंसेक्ट की डिस्टेंस यहाँ ओरिजिन से होगी R1 प्लस R2 दैट इज इक्वल टू कैपिटल R, राइट। और यहाँ पे सेंटर ऑफ द डिस्क यहाँ पे होगा x इक्वल टू 0 पे, और सेंटर ऑफ मास की पोजीशन होगी R1। तो हम लोग यहाँ लिखेंगे R1 इज इक्वल टू कैपिटल M मल्टीप्लाइड बाई 0, इसका सेंटर ऑफ मास 0 पोजीशन में, प्लस स्मॉल m मल्टीप्लाइड बाई R1 प्लस R2 डिवाइडेड बाय टोटल मास, कैपिटल M प्लस स्मॉल m। तो ये वैल्यू आ जाएगी हमारे पास स्मॉल m R डिवाइडेड बाय कैपिटल M प्लस स्मॉल m। तो ये रेडियस पर रोटेशन होगी डिस्क की, राइट। नाउ लेट अस कैलकुलेट द रेडियस ऑफ रोटेशन ऑफ द इंसेक्ट। R2 कैलकुलेट करें। तो जिस तरह से हमने यहाँ पे कैलकुलेट किया R1, उसी तरीके से हम लोग R2 कैलकुलेट कर सकते हैं। द रेडियस ऑफ रोटेशन ऑफ द इंसेक्ट इज इक्वल टू डिस्टेंस ऑफ सेंटर ऑफ मास ऑफ द सिस्टम फ्रॉम दिस पॉइंट टू द इंसेक्ट, राइट। तो ये वैल्यू हम लोग R2 लिखें, तो R2 की वैल्यू क्या हो जाएगी, कैपिटल M मल्टीप्लाइड बाई कैपिटल R डिवाइडेड बाई स्मॉल m प्लस कैपिटल M। तो ये हमारे पास रेडियस ऑफ रोटेशन हो जाएगी। तो अब हमारे पास पूरे क्वेश्चन का कंक्लूजन क्या आया कि सेंटर ऑफ मास मूव नहीं करेगा। क्यों नहीं मूव करेगा, क्योंकि इसमें हॉरिजॉन्टल डायरेक्शन में कोई भी एक्सटर्नल फोर्स नहीं है, और सेंटर ऑफ द डिस्क एंड insect both rotate about the center of mass with the different radius। तो यहाँ पे दोनों अलग अलग सर्कुलर पाथ में ये मूव करेंगे। ओके।